let's continue with confidence intervals. In section 8.1, we're still assuming that we know the population standard deviation. And remember, that's a bit unrealistic because if we're trying to estimate the population mean, it's usually not likely that we know the population standard deviation, but we're still going to assume it just for right now. Anyway, last time we used confidence intervals to estimate the population mean given an SRS, or simple random sample of size n. Remember, we're always assuming our samples are random. If they're not random, then they don't work. This whole thing doesn't work. And again, we're assuming that sigma is known, right? We're estimating mu, and then we get a sample mean x bar with a sample of size n, and we're assuming that sigma is known. All right, now two things we need to assume in order for this to work, in order for us to be able to do this process. Number one, the sample is random, like not convenience, random. And then either the sample is large, which means over 30, or the population is approximately normally distributed. Right, because then in that case we can have even small samples. The central limit theorem, right, is guiding this condition right here. That in order for confidence intervals to work, in order for the sampling distribution to be normal, and hence in order for us to be able to take confidence intervals and all that stuff, we have to have conditions 1 and 2. Also, remember the formula for the confidence interval is, I guess you would say call it the X, or maybe I guess I'll call it the X% CI is the interval with X bar minus the margin of error to the X bar plus the margin of error. Maybe that's a little wacky, and maybe I'll call this like, I guess really what it is actually is it's 1 minus alpha. That's really the term that they use. Really, it's really actually, if we're going to be technical about this, this is a little technical, but it's technically 1 minus alpha times 100%. Okay, whatever. Anyway, what is this really? This is going to be x minus z alpha over 2 times the standard error to x bar plus z alpha over 2 times the standard error. And just a quick recollection that the standard error, of course, is the standard deviation, which is the population standard deviation in this case, over root n. Right? So we need to know this formula. Right now, I guess in theory, in order to calculate the confidence interval, you don't need to know this formula because you can just plug stuff into Excel. However, we are going to learn something today that does require you to know the formula for the margin of error, right? So just to point out here in parentheses that the margin of error equals our critical value times our standard error, right? Which is our critical value times sigma over root n. Just to keep that in mind, okay? Just keep that in mind. Now, anyway, remember that the confidence level, which is we call 1 minus alpha, affects the length of the confidence interval. A higher confidence level means a longer interval, right? Because a higher confidence level means that we are more certain that the true mean is within our interval. That if we were to repeat this sample multiple times, over and over and over again, more of if the higher our confidence level is, more and more of the time, the true mean will be within our confidence interval. So this is an example that I took from the book, right? In the left picture right here, these are 70% confidence intervals. And what was it, like 50 or so of them were taken. And roughly, as we can see, if the true mean, mu, is that black line, roughly 70% of the time, that black line is a value within those little blue intervals, right? Note that they all have the same length. But sometimes, like, this guy, right, it's way off, right? It does not include the mean. Now, with the 95% confidence interval, that's what we've got in this sensor picture right here. Most of the time, right, 95% of the time or so, mu is within the interval. Mu is within the interval. But there are still some times where, it's not. And then there's a 99% confidence, a 99% confidence interval over here. And here, I think all of the time, mu is within the interval. Even in that example down here, mu is still within that interval, right? Now, what's the trade-off? Well, the trade-off is that the interval is longer, so it's not as clear what mu would really be because you've got a bigger range to work with. So that's sort of the thing that we have to weigh when creating confidence intervals is we want them to be long enough so that they will usually include the mean, but we want them to be short enough so that the range of estimates for the mean is meaningful, right? Remember we were talking about battery life for laptops. If I create a 99.99% confidence interval, but the range of estimates was like, well, it's somewhere between 2 and 18 hours of battery life, that wouldn't be very helpful, right? So that's something that we have to keep in mind. Another quick demonstration of this is if we go into Excel, give it a sec here, and we take a look, you go to the demo CLT and CI worksheet. If you take a look, we actually do that right over here, right? We set the confidence level. Here we make it 0.95, and we see how often the confidence intervals contain the population mean, which in this case is set at 40. Now note that in this case, you might say, well, it's a 95% confidence interval, only 88% of them are actually in the interval, right? If we just look down here, right? Well, number one, there's a little bit of luck involved. Number two, look at this small sample size. Remember, we need our samples to be 31 or greater in order to ensure that this process works the way it's supposed to. Because, for example, we're considering a left skew distribution, right? So let's see what happens as our sample size increases to 10. All right, well, still not great, right? We still have, only 87% of the confidence intervals containing the true mean. What if we just sort of increase this to 20? Oh, that's looking, actually, that was really good. 97% of them include the mean, right? 30, right? And then if we even go to above 30, like, 40 or something like that, you see here, 95% confidence interval, 95% of these intervals on the left here contain the true mean. But, like, for example, in this interval, right, we're off, right? This interval, right, I guess that's here. We're a little bit outside. A little bit outside, a little bit outside. Okay? So that's just a demonstration for you, okay? Just a demonstration of why we care about the percent, right, the confidence level of our confidence interval, okay? So let's just consider example 1, right? Problem 37 from the book. Just took it out from there. Construct a 95% confidence interval for mu based on the sample mean or point estimate and population standard deviation, and of course the sample size, because we need to know all that. So if we just take Excel, we put it over here, we go to one sample Z. Well, we have our sample mean, which is 7.92. Population standard deviation, 2.5, and the sample size is 10. And I guess last but not least, they do say a 95% confidence interval, so make sure to put the 0.95, right? 0.95, right? And sure enough, we get our confidence interval, okay, right? It gives us our standard error, critical value, margin of error, blah, blah, blah. So we can just say 95% confidence interval equals 6.37 to 9.47, right? We just put it into Excel. And just remember, not that you would need to write this on a quiz or something, but just remember how we got that. This is 7.92 minus, where's the margin of error? 1.55 to 7.92 plus 1.55. Right, and this guy right here, that's your margin of error. Okay. All right, now, next up it says, if the population were not approximately normal, would this confidence interval be valid? And the answer is no. Why? Why? It's because of that. Because n equals 10, which is less than or equal to 30. So, by the CLT, central limit theorem, the sampling distribution, right, of our sample mean, of our sample mean, may not be normally distributed. And so we can't use this process. We use this process only if the sampling distribution is normally distributed. Okay? So let's just take a look at the confidence level. Let's spend a couple of minutes talking about that. We've seen that we can decrease the margin of error by, well, we can do a couple of things. I guess you would say decreasing our critical value, z alpha over 2, and I'll just say, i.e., decreasing our confidence level. Whoop. Which is, we denote with 1 minus alpha. But this increases the likelihood of mu being outside our interval, which means that our confidence interval was not an accurate estimate of the ranges of mu. The other way to decrease the margin of error that does work perfectly, it just, if you can manage to do this, is to increase the sample size n. But remember, we have to ensure that our samples are random. And so logistical concern, resource concerns might put a limit on the size of our samples. But remember, if we can get to 31 or higher, then we're good to go. But if we still feel like our confidence interval is too long, the range of possible values from mu is too great, then we just need to get that sample size up. You need to sample more individuals. Okay? And anyway, this is because the margin of error, which remember equals the standard error. Actually, let me put the critical value first. This times the standard error, which remember equals the critical value times sigma over root n decreases. And that should make sense, right? As n increases, standard error should decrease. Let me just write that. Okay. So anyway, they say redo example 1 for n equals 20. Let's see what happens to the length of the interval. Well, let's go back into Excel. And we just change this to 20. 6.82 and 9.02. So I'll just say 95% confidence interval now equals 6.82 to 9.02, and this is because we have 7.92 minus, what was our new margin of error? 1.1. Right? Our margin of error decreased. Because n increased. Okay. And now you could say, well, we had a margin of error of 1.1. Would have been nice if we had a margin of error of, let's say, 1. Well, how could we do that? Well, there are two ways to do it. Number one, you could just guess and check through Excel and just say, I want it to be 1, so let's try 30. Oh, okay, I guess that was too many. 25. Ooh, that's pretty close. Okay, let's try 26. I went them with the other way. Try 24. Ooh, 1. But then even then, it's, well, is it exactly 1, or are we rounding or whatever? So it looks like our, let me just screenshot this real quick. Right, that was the guess and check method. Never recommended except as a last resort. But it is, in a pinch, a way to get things done. All right, so on the one hand, you could say, let's put this over here and say, guessing and checking suggests n equals 24. But let's see if we can use maybe a better approach to this. Well, what we can do is we can say, recall that margin of error equals our confidence level times our standard error, which is our confidence level, or I should say, sorry, our critical number times our standard error, which is our critical number times sigma over root n. So if we want, let me actually move this up here. If we want to know the value of n that will give us a margin of error that we want, then we should solve for n. Right? So if we solve for n, I'm going to multiply both sides by the square root of n and divide by the margin of error. So basically, I'm just going to swap the margin of error and root n. And we get root n equals our critical number, critical value, times sigma over the margin of error. And then square both sides to get n is going to equal z alpha over 2 squared times sigma squared over margin of error squared. By the way, I never remember this formula at all. I never remember it. I just start with the margin of error formula and then go from there. Okay? Now, this is a lower bound for n. So really, we should go to this equal sign and make it greater than or equal to, greater than or equal to. Because if n is 20, 25, or 26, or whatever, then it's actually less than 1. Margin of error is actually less than 1, and that would be great, right? So anyway, a lower margin of error is always better, right? It's always better. It means there's less uncertainty. Our interval is shorter, okay? So for this problem, we would say for margin of error, for desired margin of error equal to 1, we have n is greater than or equal to. Now, we need our critical value. And if we go to our critical value, see how it's 1.96? So maybe I should say, for margin of error 1, and 1 minus alpha equals 0.95, right? Because now we know that we have a critical number of that, right? So we have 1.96 quantity squared, right? That is our, I'll just use this guy, z alpha over 2 quantity squared. And then our sigma squared I'll make blue, times, what did we say our population standard deviation was? 2.5 squared. And then I guess we're dividing by our margin of error squared. Oh. But our margin of error, they said, oh wait, that's right. They said that was 1, right? We assumed that was 1. So we're just going to do one of these guys. Right? That's by assumption. All right, so anyway, when we work all this out, what are we going to get? Well, you can just, we've got a little blank playground in Excel. Let's just go over here. So, you can use Excel as a calculator, right? You just do equals and then just do your calculation. Equals 2.5, oh, sorry, I should say equals 1.96 squared times 2.5 squared over 1 squared. But that doesn't really do anything, right? And look at that. Oh, we get 24.01. Now, this is interesting because let's see what happens. 24.01, this means that the value 1 here is rounded, but actually incorrect. Actually, I shouldn't say incorrect, I'll say rounded but greater than 1. And that's a problem because that means that 24.01 is really not good enough, right? We can't have 24.01 people. 24 individuals that we sample will not give us a margin of error of 1. It'll give us something a little bit bigger than 1, which we don't want. So round up always. Even though it's 24.01, we say rounding up, gives n needs to be greater than or equal to 25 individuals. And that is our answer. Not 24, 25, right? So just by randomly guessing, we did not get the correct answer. So we really do need to use this formula because there might be a rounding error. Okay? Now, in general, here's the formula, right? The number of individuals and to create a confidence interval with the appropriate confidence level, blah, 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 is going to be, well, I'm just going to copy this formula down. N is greater than or equal to the confidence level squared, or sorry, I should say the critical number squared, times sigma squared over the margin of error squared. And the proof, and I'll just say where we got this from. If the margin of error equals z alpha over 2 times sigma over root n, I guess you'd say if it needs to be, I guess you'd say, I guess you would say if it's less than that, that implies that square root of n needs to be greater than or equal to, I guess we'll just, I think the inequality works. I think it works this way. Yeah, right, because root n is, yeah, we're fine. So anyway, we have that, and then we have this. And then that leads to this. Oh, sorry, no. And there we go. Okay, one more example. You can pause and read example 5. Right, but what we can do is we can note that n equals 75. X bar equals 50.1 seconds, I guess, if we care about units. And we have that sigma equals 10 seconds. Okay, so that's what we should get from that, right? Construct a 95% confidence interval. So again, this is just putting stuff into Excel. Remember to go to your one sample Z. Make sure we're set at 95. We are. This was 50.1. This was 10. And this was 75. So we have our confidence interval of 47.87 to 52.36. Is that 87? What's that? No, 84. 47.84 to 52 point... Was that 86? No, 36. Okay. So that's what we got for that. Now for part B, find the sample size needed so that a 98% confidence interval will have margin of error of 1.5. So just using our formula, and again, if you don't memorize it, that's fine. Just start with a margin of error formula. But we need n to be greater than or equal to z alpha squared over 2 squared times sigma squared over the margin of error squared. And this equals, well, by assumption, if we have a 98% confidence interval, we just go over here and put in 0.98. And we see our critical value is 2.33. Squared, of course, we square it. Times sigma squared. Okay, well, that's 10 squared. And then our margin of error, well, that was desired to be 1.5, right? Maybe I'll use a highlighter just to point that out. All right. And then if we just do this out, and let's just go to Excel, bang it out in a calculator. So we'll just say equals, and I think it was, well, actually, I don't remember what it was. 2.33 squared times 10 squared divided by 1.5. 0.5 squared. Nope. 0.5 squared. 241.3, whatever. We're going to round it up. 241.3. And that becomes 242. Right? So n needs to be at least 242. And that's what we've got.